In this video, let's do a quick review of this reading sample moments. This is FRM Part 1, Book 2, Chapter 5. Let's begin with population moments. Let me assume that I have access to an entire population, let's say one which contains these many members. For all these population members, let's say I have observed the value of a variable capital X, and I can use this information to calculate both the expected value of X denoted by mu and the variance of X denoted by sigma squared. Mu and sigma, these are parameters which are associated with the entire population. For mu, basically we calculate it as the simple average of the observed values of X across all population members. Sigma squared is also calculated as a simple average. It's the simple average of the squared deviations of X from the mean mu, and again it's computed across all population members. Okay? In practice, please note that we do not have access to the entire population, and hence we work with a rather small sample, let's say, whose size is denoted by lowercase n. We use the information which is coming from the sample to estimate the parameters for the entire population. The formula which we use to estimate any given population parameter, that formula itself is called the estimator, and once you apply any given estimator to a given or chosen sample, what comes out is a point estimate of your chosen population parameter. Okay, for let's say the mean mu, our estimator would look something like this. It's denoted as mu, the parameter, with a hat on top. Again, it's a simple average, but this time the averaging is being done across the members of your sample. When you apply this estimator to a given sample, this is what comes out. This is the point estimate of the population mean mu. Okay? Again, you have an estimator for sigma squared as well, written as sigma hat squared. It's again a simple average. Simple average of the squared deviations of x's which are coming from the sample, and these are deviations from the sample mean mu hat, and this simple average is being computed across the n members of your sample. Now this estimator, as we will very quickly note, is not 100% correct. It needs a tiny correction, but as of now let's just assume that it gives us some estimate of the population sigma squared, and if I were to take that estimate and take a square root of it, what I get is the estimate for the standard deviation of X, which is sigma. Okay. Next, let's talk about bias of any given estimator. Let's say I have an estimator for a population parameter theta. The bias of this theta hat is simply equal to the expected value of theta hat minus the true value of this population parameter theta. You can think of the expected value of this theta hat to be its average value when this estimator is applied to, let's say, many samples. If I were to talk about this guy, the estimator for mu, then please note that if all your sample observations they come from the same distribution, then this estimator is an unbiased estimator. One can prove this, that the expected value of this mu hat is actually equal to the population value of mu. Okay, and hence the bias for mu hat is equal to 0. On the other hand, if I were to try and calculate the bias for sigma hat squared, then the expected value of this sigma hat squared, actually it comes out to n minus 1 over n times sigma squared. So it doesn't come out to be equal to sigma squared. Putting this into our bias formula tells me that the bias for this estimator is minus sigma squared over n, which means that the estimates coming out from this estimator are biased downwards because of this negative sign. To make our estimator for the population variance unbiased, what we can do is that instead of working with n in our denominator, we can work with n minus 1, and let's rename our estimator to be s squared. Okay, s squared, please note, is an unbiased estimator of sigma squared. Let's come back to mu hat. So if your sampled values are IID, which means that they are independent and identically distributed, the variance of this mu hat would simply be equal to sigma squared divided by n. Taking a square root, this tells me that the standard error of mu hat is sigma over square root of n. Mu hat, please note, is a linear estimator. It linearly combines the values which come from any given sample. We've also noted that mu hat is an unbiased estimator. From the universe of all linear and unbiased estimators, mu hat turns out to be that estimator which has the lowest variance, and hence mu hat is also called blue, best linear unbiased estimator. If you were to expand your universe of estimators and also include estimators which are, let's say, not linear, you will find that the maximum likelihood estimator actually has a lower variance compared to this mu hat. But the MLE estimator is not linear and it tends to be biased as well. Next, let's take a look at the large sample behavior of mu hat. Please note that law of large numbers applies to mu hat, which means that if your sampled values of x are IID, independent and identically distributed, then for large sized samples, the estimate of mu almost surely converges to the true value of mu. If law of large numbers applies to any given estimator, then it also means that that estimator is consistent. Being consistent means that the estimator, it satisfies two properties. Number one, although your estimator can have a bias if the size of your sample is finite, as the size of your sample increases, your estimator, it becomes asymptotically unbiased, which means that for very large sample sizes, your bias vanishes if your estimator is consistent. The second condition is that as the size of your sample increases, the variance of your estimator also converges to 0. Okay? Then let's talk about central limit theorem. So if a few conditions are satisfied, central limit theorem tells us the distribution that our mu hat will follow, the distribution that mu hat will converge to. The conditions are your xi sampled values of x should be IID, they should be independent and they should be identically distributed. They should be drawn from the same distribution, it can be any distribution, and all values of x should have the same mean mu and a finite variance sigma squared. Let the size of your sample be big enough. Let it be huge. In practice, all we need is actually your size of your sample to be greater than or equal to 30. Okay? If these conditions are satisfied, central limit theorem tells us that the distribution of this standardized variable, which we have created by taking our mu hat, subtracting from it its expected value, which we know is mu, and dividing the difference by the standard error of mu hat, which is sigma over square root of n, this standardized variable converges as far as its distribution is concerned to the standard normal distribution. Specifically for mu hat, it means that if these conditions are satisfied, its distribution converges to the normal distribution with mean mu and standard deviation sigma over square root of n. That means I can write down mu hat to be mu plus sigma over root n times the standard normal variable z. Okay. Next, let's talk about other measures that can be estimated using your sampled data. So using your sample, you can also estimate the skewness of x using a very simple formula, very simple estimator that looks something like this. So in this estimator, skewness is being estimated as the simple average of the cubed deviation of the sampled values of x from the sample mean mu hat divided by the cube of the sample standard deviation sigma hat. I am assuming in this estimator that I am working with a large enough sample, and hence even though this estimator may be biased, I am not required to make any corrections to remove that bias. Similar to this formula, I can have an estimator for kurtosis as well. The only changes required would be in the numerator, we will have this exponent to be 4, and in the denominator, your sample standard deviation would also be raised to the power 4. Okay. Now, if you want to use your sample to, let's say, estimate a quantile based on, let's say, a given probability alpha, all you have to do is you have to sort your sample values from the smallest to the largest and pick the quantile corresponding to alpha to be that value which is sitting at the n alphath position counted from the left. If n alpha is not an integer, you will have to average the values which are sitting at positions which are to the left and to the right of n alpha. Next, let's talk about median, which we know is the 0.5 quantile. To estimate the median, again sort your sample values from the smallest to the largest, and if your sample size is odd, pick the median to be the value which is sitting at the n plus 1 over 2th position counted from the left. If your sample is even, sample size I mean, then you can estimate your median to be the average of the values which are sitting at the n over 2th position and n over 2 plus 1th position counted from the left. If you want to estimate your interquartile range, very simple, just estimate it to be the difference between the 0.75 quantile estimated from your sample and the 0.25 quantile again estimated from the same sample. Okay. Next, let's talk about cross moments. If let's say you have a sample which has these many members in it, and for each of these members you have observed a pair of values x and y, then you can use this information to estimate the covariance between x and y. The estimator would look something like this. Covariance would be estimated as the simple average of the product of the deviation of x from its own sample mean and deviation of y from its own sample mean. This estimator may also be biased the same way as this estimator was. And to correct for the bias, all you have to do is you have to replace this n by n minus 1, the same way as we did here. Okay. Once you know the sample-based covariance between x and y, you can actually scale this covariance by the standard deviation of x coming from the sample and standard deviation of y coming from the same sample to get an estimate of the correlation between x and y. Okay. Then, if x is individually IID and y is also individually IID, and we are talking about a large enough sample, then you can write down for x and y, I mean for the sample means of x and y, the bivariate version of the central limit theorem. All it says is that if proper conditions are met, the distribution of this 2 cross 1 vector of sample means converges to the bivariate normal distribution with this vector as the mean and this 2 cross 2 matrix as the variance covariance matrix. All it means is that the mean value of this mu hat x is mu x, its variance is sigma x squared over n, mu hat x can be assumed to follow the normal distribution. The mean value of mu hat y is mu y. Its variance is sigma y squared over n. Individually, I can assume this guy also to follow the normal distribution. The covariance between these two is given by sigma xy, the covariance between x and y divided by n. The correlation between x and y is the same correlation between the sample mean of x and the sample mean of y. Okay, so the correlation between x and y transmits exactly to be also the correlation between the sample mean of x and the sample mean of y. Okay. The last topic for this video is Coskewness and Cocortosis. These are higher order cross central standardized moments. So when it comes to Coskewness, it's a cross version of skewness. I know that in skewness, both in the numerator and in the denominator, I have an exponent of 3. When I define a cross version of skewness, I will let this exponent of 3 be collectively contributed by the two variables involved, which are x and y. When there are two variables x and y, I can have two types of coskewness. In the first type, x contributes 2 powers, y contributes 1 power. In the second type, x contributes 1 power and y contributes 2 power. In both these cases, therefore, my total power is indeed 3. Okay, how do I interpret coskewness? I can interpret coskewness to be the likelihood, actually to be a measure that tells me the likelihood of one variable having a move in a given direction when the other variable, one which contributed 2 powers, experiences a significant deviation from its own mean, and that deviation can be in either direction of the mean. For example, if this coskewness is positive, it means that whenever x experiences a high deviation from its mean in either direction, there is a high chance that y will experience a positive deviation from its mean. Why? Because this coskewness is positive. Okay? Then, let's talk about cokurtosis. Again, it's a cross version of kurtosis. The total exponent required is 4, and we can, for two variables x and y, define 3 types of cokurtosis. This is the symmetric type of cokurtosis, one in which both x and y, they contribute powers of 2 each, making the total power 4. These are asymmetric versions of cokurtosis in which x and y contribute unequal number of powers. In this cokurtosis, x contributes 1 and y contributes 3. In this cokurtosis, x contributes 3, y contributes 1. Okay? How do I interpret this symmetric cokurtosis? This cokurtosis is the measure of dependence between extremes of one series, that means one variable x, and the extremes of the other series, that means the other variable y. Okay, so here I am talking about extreme values irrespective of which direction these extremes happen in. I mean direction with respect to the mean value. Okay, then coming to asymmetric cokurtosis, these can be taken to be measures that tell you the dependence of, let's say, the sign of the deviation of one variable when the other variable, one which contributes 3 powers, experiences a large deviation in a given direction. If, let's say, for example, this cokurtosis is negative, what does it mean? It means that if y experiences a very large negative deviation, which makes y move to its left tail, because this cokurtosis is negative, there is a high chance that x will experience a positive deviation from its own mean. Okay? Now, before I stop, let's very quickly take a look at the values which these cross higher order measures take when x and y, they have the bivariate normal distribution. If x and y have the bivariate normal distribution, please note that irrespective of the correlation between x and y, these two coskewness measures They both turn out to be equal to 0. If x and y follow the bivariate normal distribution, cokurtosis show a dependence on correlation between x and y. For this symmetric cokurtosis, this is how the variation of this guy with respect to rho, the correlation is. It's a U-shaped plot. If rho is equal to 0, this cokurtosis reaches its minimum value, which is 1. If rho is either plus 1 or minus 1, this cokurtosis takes on its maximum value, which is 3. For asymmetric cokurtosis, this is how the plot looks like with respect to rho. When rho is 0, this asymmetric cokurtosis is also 0. When rho is plus 1, this guy would be plus 3. When rho is minus 1, this guy will be minus 3. Okay? This video was a quick review of this reading sample moments.